Hello and welcome back to this course. So last class we dealt about the different aspects of electrochemical energy. We started with Gibbs free energy and its significance. Then we moved on to its dependence on the pressure and temperatures, and ultimately we also found out a relation between Gibbs free energy and the electrical potential, which are very linearly related with the parameter Nf, whereas N is your number of moles of electrons and F stands for the Faraday's constant. Then we moved on to dependence of this Gibbs free energy or the potential on concentration, and that's how we led to the Nernst potential, which is basically, as we can see here, it is E equals E naught minus RT by NF ln of activity of products. That is, in case of hydrogen oxygen fuel cell reaction, your water is our product and H2 and O2 are our reactant species. So, the Nernst potential can be written as E naught minus RT by NF ln of activity of water divided by activity of product of activities of hydrogen and oxygen. Same relation can also be written in terms of electrolysis reaction, wherein the water is the input and hydrogen and oxygen are outputs. So, in that case your Nernst potential can be written as we can see on the right side, it is minus 1.23 minus RT by NF. So, N is 2 here and ln of products by reactants. So, products are our gases. So, that is why the activity is nothing but the pressure of hydrogen multiplied by pressure of oxygen raised to half. So, half comes there because we have half mole of oxygen getting evolved there, and this 1.23, as we have seen, it is a reversible cell potential of fuel cell or the electrolysis at standard temperature and pressure conditions. So, standard temperature and pressure conditions, as we know, it is 1 atmosphere and 298.15 Kelvin, and at this temperature and pressure the potential that we observe is 1.23 volt. We will also go ahead and calculate that. So, as we can see here, in case of Nernst potential, the pressure of the gases as it increases, as I have already written here, the potential also increases, but this increment is not much. How that is the reason? There is a reason, because this pressure increment or decrement, they are logarithmically connected with the potential rise or fall, and that is why increase in the pressure does not linearly increase the pressure also, and that is one of the reasons why fuel cells are not operated at much pressures, because there is not much gain that we get in the potential. However, this temperature, as we can see, it exists in this Nernst potential, and this does not fully account for the changes in the potential. That is why we went ahead and we wrote the Nernst potential as, so we can write En as equals EP comma T, that is Nernst potential at any arbitrary pressure and temperature, which is also equal to ET. Now, ET is the reversible potential or potential at the arbitrary temperature T, where T is not equal to T naught, or it's any other temperature other than T naught, minus RT by NF. The rest of the components in the equation remain same, and this ET is again, you can say, is equal to E naught plus entropy change divided by NF multiplied by change in the temperature. What is the temperature that with which the cell is deviated, or at which it is operating? So, the T stands for the operating temperature of the cell, whether it is a fuel cell or electrolyzer, and this entropy stands for the entropy change at standard temperature and pressure conditions. This 0, as you can see, this 0 stands for, it is at STP, and plus the integration of heat capacity over temperature for the given temperature range. So, let me write this up here. This STP, standard temperature pressure condition, is standard temperature and pressure condition which is nothing but 1 atmospheric pressure, that is for pressure, and temperature is 298.15 Kelvin. So, this is what the standard temperature and pressure conditions mean. We can also approximate it at 1 bar. This can be approximated as 1 bar and 298 Kelvin. So, because 1 atmosphere is nothing but 101.325 kilopascals and 1 bar is nothing but 100 kilopascals. So, there is hardly any slight difference that we can see, and hence the STP can be approximated as 1 bar 298 Kelvin. So, whatever potentials that we show or write, if they are with respect to standard temperature pressure conditions, they can be written as E naught, or whenever we write in terms of energies, we can write it as delta G naught or delta H naught. So, this naught represents the standard temperature pressure conditions. Anyway, so this is all about how we can find out the Nernst potential at different temperature and pressure conditions. Let me quickly elaborate this equation number 3. So, as we can see, this entropy change is dependent on the heat capacity, which is also a function of temperature, as I have already mentioned before. T naught to T. So, this heat capacity, as we have discussed, this is in case of liquids or solids, does not vary much. So, Cp is almost constant as in case of solids and liquids. However, the Cp is highly a function of this operating temperature or temperature in general. So, when we deal with the gases, as they are very loosely connected with each other, when we change the temperature of these gases in which they are surrounded, their entropy is changed, because there is a lot of you can say energy that is getting added or subtracted depending on what temperature we operate at, and that is why it is very important for gases that we consider this entropy change. And this expression, this third equation number 3 particularly is exclusively written or used for reactions that involve gases. So, how does it look like in case of our conventional hydrogen and oxygen reaction? Let's say I take fuel cell reaction, wherein H2 plus half O2 gives H2O. It's our standard hydrogen oxygen reaction. This Cp for, let me say, for hydrogen. So, this Cp, as I was talking about, this depends highly on the temperature, its function of temperature, and how it can be written in case of water. Let me start with water. So, it is nothing but it is 143.05 minus 58.040 T to the power 0.25 plus 8.275 T to the rest to half minus 0.036989 times T. This is in case of water. How we can write it for hydrogen? It is 56.506 minus 22,222.6 times T to the power minus 0.75 plus 116,500 divided by T minus 560700 times T to the power minus 1.5, and Cp for watt oxygen is 37.432 plus 2.0102 into 10 to the power minus 5 times T to the power 1.5 minus 178,570 times T to the power minus 1.5 plus 2368800 times T to the power minus 2. So, this is what heat capacity depends on temperature. As you can see, it's almost every the number has some function T there. And how does it vary if I try to plot it with respect to temperature? So, this is Cp of water, so it slightly increases like this, and if I plot in terms of temperature for hydrogen, it merely it increases and then merely becomes constant. In case of oxygen, it again goes just like in case of water, so it increases. So, we can plot this as and when we change the temperature, and we may expect a similar curves or similar graphs in case of water, hydrogen and oxygen. So, what we have to do here is we have to, when we want to calculate the Nernst potential at different operating temperatures and pressure, we have to, first thing we have to do is we have to find out the entropy change for the reaction, which is given by equation 3, and then once we find out the entropy change, we have to substitute back to equation 2, wherein we can find out the ET. So, once we find out ET, we have to again substitute back to equation 1 and then find out Nernst potential. So, let us go ahead and solve some examples. Let us start with a basic example. Let us take our conventional hydrogen oxygen reaction converting to water, and what we have is enthalpies and the entropies at STP for all these chemical species. So, enthalpy for hydrogen is 0 and as well as for oxygen is 0, because it is believed that they exist in their natural form in this universe. So, there is no enthalpy of reaction concerned to those species. For water, it is minus 286 or 285.8 is also okay. So, kilojoules per mole, and or we can also write kilojoules only, because this is an extrinsic property that we have written delta capital H. So, what is the case in case of entropy? It is 130.08. Then we have for oxygen it is 205.14, and entropy for the water is around 69.91. This is joules per mole per Kelvin, K is capital here. So, let us first find out the reversible cell potential using this data. So, what is our enthalpy of the reaction? Enthalpy of the reaction is nothing but, as we have already discussed this before, enthalpy of the products minus enthalpy change of the reactants. I can also write this as delta H naught P minus delta H naught of R. So, what is our enthalpy of the product? It is minus 286 kilojoules per mole, minus enthalpy of reactants is 0 plus half times 0. So, that will come as minus 286 kilojoules per mole. So, this is our, let me write this as an intrinsic property. So, let me write as delta H naught Rxn. Okay. So, this is how we can find out the enthalpy of the reaction as minus 286 kilojoules per mole. As we can understand, minus stands for it is an exothermic reaction and heat will be evolved. So, this is the maximum energy content that we have. Now, what we do next is, let us also find out the entropy of the reaction. When I say reaction, it is the hydrogen and oxygen getting converted into water. So, let me write delta S reaction as delta S naught products minus the reactants. Sorry, I should write as entropy of products minus entropy of the reactants, and that brings close to, so as we can again write it as 69.91 minus 130.08, that is for hydrogen, entropy of hydrogen, and then we have plus half of, since half because we have half mole of oxygen there. So, half times 205.14. So that gives us, as if we solve this, it will come close to minus 162.74. This is in joules per mole per Kelvin. So we have, so as we can see, entropy change is negative, which means as we have already discussed this, there is less, you can say, the heat, that is basically all the heat is getting released because of the change in the gases to liquid. So we don't, since we do not have any gases on the product side, considering water as a liquid in the liquid phase, so the gases, that is 1.5 mole of reactant species, are getting converted into products, and since there is a less chaos at the exit, we can, that is why we can get entropy change as negative. So let us move on and let us find out the Gibbs free energy. We know that it is H, enthalpy is nothing but Gibbs free energy plus entropy change. So we can rewrite this as delta G naught as delta H naught minus T delta S naught. So once we substitute this, as this is minus 286, this is all in kilojoules. So we need to convert this into joules. So times 1000. This is also T naught. So we are all considering at standard temperature pressure conditions, which is 298.15 times, what was that? It is minus 162.74 minus 162.74. So if we calculate this, this comes somewhere close to minus 237,000 joules per mole. So this is in Kelvin, temperature is in Kelvin, and entropy is joules per mole per Kelvin. So that Kelvin gets cancelled and we get normalized unit as joules per mole. We can also write this as in intrinsic values. So delta G naught of reaction. So what we know from previous studies is this reversible or any potential is nothing but your Gibbs free energy divided by NF. So since we are dealing at STP, this is G naught. So this E also has to be E naught, and so this delta G naught, as we have just found out, it is minus, so there is a minus here. So minus of, what is delta G naught, is basically minus of 237,000. This is in joules per mole. Let me write the unit as well. N is, it is a hydrogen oxygen reaction that involves 2 number of moles of electrons. F is Faraday's constant, so it is 96,485. This is in coulombs per mole. So that is the unit of Faraday's constant. So if you can see, this mole and this mole gets cancelled, and what we get here is joules per coulomb. So that is the energy invested to bring 1 coulomb of charge. So that is nothing but unit as voltage, and this minus minus becomes plus, and if we find this, calculate this, the equation, we get 1.228 volt, which can be written as 1.23 volt. So that becomes our E naught. Sorry. So this is your reversible cell potential. So this is what the reversible cell potential of a fuel cell reaction that involves H2 and O2. No matter what materials are used in that fuel cell, if that is H2O2 fuel cell, it has to have a standard reversible cell potential as 1.23 volt. And we can also sort of find out for the electrolyzers how it will be in case of electrolyzers. As we can see, in case of electrolyzers, this delta G naught is nothing but delta H naught minus T naught delta S naught. So same equation I have used here. However, this enthalpy change, as we know from our previous studies that it is plus 286,000 joules per mole, and why plus? Because it is energy intensive process. So, what we are talking about here is water getting converted into hydrogen and half mole of oxygen. So, since it is an energy intensive process, so enthalpy change will be positive. So, which means that the energy will be required by the system to perform this reaction. Minus T naught is our standard 298.15 Kelvin, and delta entropy change will be positive. So, I can write it here as plus 162.74. So, if we solve this, this will be plus 237,000 joules per mole. So, this is your delta G reaction. So, plus 237 means the energy will be required by the electrolyzer to basically perform that reaction which we have written here, and rest of the process remains the same. So, if you want to find out E naught, it is minus of delta G naught reaction by NF. So, if I simplify this, it is minus of delta G is plus 237,000 joules per mole, and same thing will be at the denominator 2 times 96,485 coulombs per mole, and this again comes to this plus and minus becomes minus 1.23 volt. So, that way we can say that reversible cell potential for the electrolyzer at STP. So, this is all at standard temperature and pressure conditions, which is, again let me write it down, 1 atmosphere and 298.15 Kelvin. In case of fuel cell, it will be plus 1.23 volt. So, if you are experiencing or if you are coming across any cell potential of any reaction which is positive term, that means the reaction is exothermic, and if the potential, as we can see on the right, if it is negative quantity, it means then the reaction is endothermic. It will require energy to basically undergo that change. So, this minus sign, all it indicates is we have to supply that energy, that potential of 1.23 to break the first molecule of water. So, that is all about finding out the, you can say, the reversible cell potential at STP, both in case of fuel cell as well as in case of electrolyzer. So, with that we will stop here and we will take on with more numericals in the upcoming class. With that, thank you.